Welcome to the lectures on fundamentals of MIMO wireless communication. In the previous lecture, we have seen the capacity of MIMO systems when channel is not known at the transmitter. So now we will take a look at the capacity when channel is known at the transmitter. So basically, with this figure that we used in the previous lecture, we now have a feedback in the system. So in brief, we could draw an image of transmitter block in general, and a receiver block in general, and there is this channel in between the transmitter and the receiver. So this channel is estimated at the receiver, so you usually write it as H cap, but if it is ideal, we would say that it is H. This H is fed back. There is feedback system, which is again an ideal feedback system. An ideal feedback system would mean that there is perfect, that means error free, and it is instantaneous, which is never a reality. So these assumptions are never true in practice. In practice, you will always get some estimation errors, as well as you will be getting delays, because that is natural. When signal is transmitted from the source, you require certain time for the frame duration, it requires certain amount of estimation signal processing time. Further, you would also require time to send back information from the receiver back to the transmitter, which will again be used during communication. So in that case, one might question that why is such an analysis being done, or why is it so important? The importance of this is to find out what if at all you have the best channel information at the transmitter, what the best can you do. So although this is not achievable in practice, at least it is going to give us hints towards what is the gain that can be achieved if such a thing is realized, which would further tell us that whether we need to do it or not, or what is the loss if you do not have the exact channel information could be further investigated. Using these knowledge, again practical schemes could be devised which would take care of errors, as well as which would work with certain amount of feedback delay. So with this background, that although what we are doing is really of theoretical interest, there lies a lot of practical message behind it, and a lot of practical designs could be driven or could be motivated based on the results that could arrive out of this particular analysis. So here again it is assumed that full channel knowledge is available. Full channel knowledge means complete H. H is a matrix. So if it is a M cross M matrix, so that means there are M squared elements, and further that each of these elements are continuous. So basically you have full value, so which is not possible, which is technically not possible, but still it's idealistic assumption, as I have already described. And we'd also consider that it's rank R, that means it's not a full rank matrix, so it's in general. So we're going to say that H is of rank R, it is zero mean, circular symmetric, complex Gaussian. We have described what is the meaning of zero mean, circular symmetric, and complex Gaussian. And this vector SR is basically S1. We usually have SMT, but now we are saying that no, this is not what we are doing. Instead, if I need to draw it again, channel number 1 up to channel number MT, right? There is some processing unit before this, and here there is S1 up to SR number of symbols which are being sent from the transmitter. So SR is the vector which will be used. Again, this is zero mean, circular symmetric, complex Gaussian. That is what we will assume. This will be multiplied. This will be multiplied with a vector V, with a matrix V. This gets multiplied with a matrix V. So there is some processing with this matrix V at the transmitter prior to transmission. So what actually goes into this is basically S tilde, which is equal to V times S. So if S is R cross 1, this has to be MT cross R, otherwise we cannot do this. So end of it, you are going to get empty cross 1 as the size of S tilde. So, we will have finally S tilde 1 to S tilde empty. This is being transmitted. So, the signal at the receiver would be our normal form y equals to h S tilde plus noise, y indicating matrices and vectors. So, S tilde is basically V times S plus noise. Right. H you could factorize into singular value decomposition. We have described that before, U, D and V Hermitian. Okay. So, it is U, D and V Hermitian. That is how you could break it into, where D is the diagonal matrix composing of the singular values. So, we have R singular values, V and U are unitary matrices containing of vectors which are of length 1. So, with this in mind, that means H could be broken down into these factors of diagonal singular values, unitary matrices over here, unitary matrices U, and it is S is what is being transmitted is pre-multiplied by V. So, what we have is D times V Hermitian times V times S. This is what we have, U. So, V Hermitian times V is basically I, D is the diagonal matrix, S plus eta. So, just by pre-coding or pre-processing with V, we have identity here. That means, there is a diagonal and there is a vector. So, that means, each of the diagonal entries get multiplied by each corresponding S. Now, at the receiver, if we would multiply by U Hermitian, what we are going to get is U Hermitian U and U Hermitian times N. So, this again U Hermitian U is identity matrix. So, this would lead us to Y tilde, that is what is being received. We go to this point is equal to D times S plus eta or noise tilde. So, U is a unitary matrix. So, even after processing, the noise variance is not going to change. So, we simply change the notation to N tilde. So, if we look at this, what is happening over here is D is basically singular value 1, singular value 2 up to singular value R, and S is S1, S2 up to SR, and this again would be N tilde 1, N tilde 2 up to N tilde R. So, what we have as Y tilde is basically each of these lines yi is equal to sigma I times Si plus N tilde I, right. This is what we are going to receive, and of course, E of N tilde N tilde Hermitian, if we take this, is going to be N naught times identity matrix of size R. This is what we have indicated over here. So, this is what we are writing. So, we have this particular received expression. We would also have to satisfy that RSS is going to the trace of RSS, or trace of RSS should be MT. That means, the total transmit power should be MT. That is what we should have. So, we get this expression. So, what this expression means is that of course, we have to just modify this expression a little bit. We have root over ES upon MT at all stages. We should have root over ES over MT, indicating the total transmit power is constrained to ES, and so root over ES upon MT is there. So, here also root over ES upon MT. So, we write the expression clearer. yi is equal to root over ES upon MT times sigma I Si plus N tilde I, right. So, yi is the ith received signal, and Si is the ith transmitted signal. So, what we see is in this form y1 contains only S1, Es upon Mt or Es upon M, Mt, we have Mt antennas over here. Sigma 1 is the singular value corresponding to the first singular value times S1 plus n tilde 1. This is a variance of n naught. So, Y1 does not have anything else other than S1. So, there is no interference between the symbols in this case. Although we had seen initially that when you send a MIMO transmission, whenever you send some things here, everything is received in all antennas. So, first antenna is going to receive S1 to SMT. However, because of the pre-processing which has been introduced here, we are not going to get any such interference. So, what we have done over here, pre-multiplied over here. So, that means there is some pre-multiplication, because of which this interference is gone and we are receiving this. So, Y2 is equal to root over Es by Mt sigma 2 S2 plus n tilde 2 and so on. So, we have clearly got them separate out, there is no interference, and we can say that H can be decomposed into R parallel channels, CISO channels, right. And if you look at what is sigma I is equal to root over lambda I, where lambda i's are eigenvalues of H Hermitian, right. So, we could write the expression as yi is equal to root over Es upon Mt times root over lambda I Si plus n tilde I equals to 1 to up to R. So, we have also achieved parallel transmission, and in this case we could write the capacity of the MIMO channel as sum of I equals to 1 to R log base 2 1 plus Es upon Mt times we have lambda I, because this is square root of lambda I. So, the square of this would be available lambda I upon n naught times gamma I, where gamma I is equal to E of Si mod squared for I equals to 1 2 up to R. So, in the previous one we had RSS. Now, even after RSS we had I over there, because each of them had a value of 1, but now we are saying that no, instead of having each of them having the same value, which we had done the case for no channel state information at the transmitter, now we have gamma I indicating that there is a certain amount of power to be given to each of the transmitted signal. However, subject to the constraint that sum of gamma I is equal to Mt. So, this constraint has to be maintained. Okay. So, now what remains for us to do is, this is good as the capacity, is to find what is the maximum value of this expression C, which would be defined as the so called capacity of the system when channel knowledge is available at the transmitter. So, till now we have said that we could give different powers to it, because channel knowledge is available at the transmitter. So, we have to work out what kind of powers can be given, because each of the channel modes can be accessible by means of pre-coding. So, we could rather write the expression of capacity or mutual information maximization problem. We could write the mutual information maximization problem can now be stated as C is equal to, you find the maximum value of I equals 1 to R log base of 2 1 plus Es upon Mt n naught lambda I plus gamma I, subject to the constraint that sum of gamma I is equal to Mt. So, this, once we solve this, we would find the values of gamma I, which would lead to the max value of this. Looking at this expression, this is a log function. So, log is concave in gamma i's. Now, this is a characteristic of the channel. So, we are not saying that we want to find what is the property of lambda I, which we did for orthogonal channels. So, we are not assuming orthogonal channels because we have already taken the rank R. So, we are saying that given a set of lambda values, that means given a set of eigenvalues, that means for or given set of lambda i's or for given set of H, can I find gamma i's which would maximize it. So, we look at the optimum maximization problem. You can derive this, but what the result is what is more important as of now. The optimum values of gamma I can be written as some mu, some constant, minus mt n naught by es lambda I. We indicate with a plus, and we also have the constraint I equals 1 to r gamma I optimum. OPT is indicating optimum is equal to mt, and mu is a constant, and this plus, that means x plus is equal to x if x is greater than or equal to 0, and 0 if x is less than 0. Now, this solution is known as the famous water pouring solution. What we will do is the exact steps for going from this to this would be written down, and it will be attached along with the videos, so that you can follow through the steps and arrive at this expression. So, the expression of mu that is usually done is we are going to give it as. So, there is an algorithm by which we will do. I will show it later, but before we go to the algorithm, let us try to see what is the meaning of it, and we will try to understand. So, let us assume as of now that mu is some constant. So, if we look at the expression of gamma I opt, so what is gamma I? Gamma I is E of mod Si squared. So, that is the ratio of the power on the ith symbol compared to all other symbols. So, if I have this, then basically I am talking about power distribution amongst the different transmitted symbols I equals to 1, 2 up to r, indicating the different modes of the channel. So, when we have this, we could write this as mu minus 1 upon Es by mt n naught times lambda I. So, what is this? So, this is some constant, take away 1 upon what is this, Es by mt is the equal power multiplied by lambda I. Lambda I is basically the channel strength, you can say, because lambda I is the eigenvalue of the ith eigenvalue of H Hermitian, or the ith mode of the channel. So, now if we take this and try to draw a figure, and say that this is I equals to 1, this is I equals to 2, I equals to 3 up to I equals to r, okay. And we have these bins, these power bins, these are power bins, okay, and say we have some level which is known as the mu. So, this is the total power, that is mu. So, 1 upon this, right, is basically, if I would write over here, lambda I is the first eigenvalue, lambda 1 is the first eigenvalue. Now, we have earlier said that lambda 1 is greater than or equal to lambda 2 is greater than or equal to, and so on. That means, lambda 1 is the highest value, rest of it is constant. So, that means, this is the smallest value, right. So, the second eigenvalue lambda 2 is smaller than lambda 1, that means, this value is bigger than case of 1. So, we have it here, this is still remaining constant. So, this is indicative of the amount of power that you are going to give. So, this is gamma I optimum to the ith symbol. So, to the first symbol you are going to give mu minus 1 upon this value. For the second, it is mu minus 1 upon this with lambda 2, and what we are saying is lambda 1 is bigger than lambda 2. So, this number, this big number is smaller for lambda 1 than lambda 2. So, basically this is the part which is Es upon mt n naught times lambda I 1 upon that. So, lambda 1. So, this is 1 upon Es by mt n naught times lambda 2 and so on. So, basically like this up to lambda r. So, this is 1 upon Es upon mt n naught times lambda r. So, what we have effectively is the remaining portion, that means mu taken away this value is the amount of power that could be associated with the ith mode of transmission. So, it is inverse of the SNR, right. So, or in other words you can say whichever channel has a large value of lambda I, you are giving more power to that particular stream. And if you look at what is happening, as if these are buckets with connection at the bottom, and once I pour water, the water gets filled up in each of the bucket according to the amount of volume that is left unused, and the volume that is used up, that means this space is basically proportional to the amount of noise that particular bucket is having, or amount of sand that bucket is having. So, rest of the bucket is filled with water, and the water across all the buckets is the same. So, that is why it is as if you are pouring water on a sequence of buckets. Can imagine it to be a sequence of buckets on which you are pouring the water, and they are connected at the bottom. So, these are connected at the bottom. So, when I pour water and suppose we have some amount of sand filled in them, in that case the level of water would be the same in all the buckets, but the amount of water that will be present in the buckets would be the level of water taken away the amount of space which is not available. So, the amount of space which is not available is inversely proportional to the SNR, or the amount of water that goes into is proportional or is related to the SNR. So, we can clearly see as lambda 1 is bigger than lambda 2, the SNR is the signal to noise ratio is bigger, or the relative noise is smaller. So, the amount of power you are putting in is more. So, more the channel strength, more the amount of power that you have to put in, and this has to be done in an iterative manner. We will give the algorithm very soon. So, this is one of the well celebrated water pouring algorithm, as we have already indicated in this particular expression over here, or what we have written over here. And in order to arrive at this, there is a particular sequence of steps that is usually to be taken. So, the way it is done is you would set the iteration count p is equal to 1, and one has to calculate capital K given by mt upon gamma minus, or mt upon r minus p plus 1 plus 1 plus n naught upon Es sum over I 1 upon lambda I equals to 1 to r minus p plus 1. R is the rank of the matrix. R is the rank of the matrix. The power is allocated to the ith subchannel and calculated as gamma I. The power you have to give is equal to K minus mt n naught upon lambda I times Es. So, this is the amount of power that is given, and this is the expression of power which we are talking about, and the explanation of this we have already given. And once you do this, so basically it is in plus. So, if it turns out that gamma r minus p plus 1, that is the particular iteration, is less than 0, that means it is negative, you reject this solution and go to I plus 1. So, you increment to the next iteration, and you carry on repeating this. So, basically you calculate this constant. After you calculate this constant, use this constant in this expression in calculating gamma I. So, once you have found the values of gamma I, then you can put them back into the expression of capacity that is over here, which is going to give you the maximum value of capacity that you can achieve. Yes. So, this is what we need to arrive at, and yeah. So, basically the capacity expression when channel state information is available would be driven by this, where you are dependent on lambda I, and lambda I the optimum values of lambda I you are going to obtain as a solution to this particular expression. So, once, so basically what we can say at the end is that suppose we have S tilde is equal to V s, right. We could say R S S optimum is equal to V times R S S optimum. So, basically R S tilde optimum times V Hermitian. This is a diagonal matrix because S are independent. So, you have R S S optimum would again be a diagonal matrix of gamma I, gamma 1 optimum, gamma 2 optimum up to gamma R optimum. Okay. So, one could view this as you are sending S1 through a channel whose strength is lambda 1, and you are adding of course noise N1 to it, but the weight you are giving to this is gamma 1. Like that, you have SR, you are giving the weight of gamma R to it. This is lambda R. So, as if you have R parallel channels. In R parallel channels, the gain of the channels are proportional to lambda 1 to lambda R, or proportional to lambda I, and you are providing amount of power gamma I to that particular channel, which is related to gamma I by the expression which is given here, which in other words means that higher the value of gamma I, more the amount of power that you should put in. So, with this we have covered two very important class of systems. One, when channel state information is not available at the transmitter. For that particular case, we do equal power transmission for all of them, where we said RSS is equal to IM of t, whereas in the case where where channel state information is available at the transmitter, we do not say RSS, that means the covariance matrix of the source symbols is equal to I, but rather it is equal to the diagonal matrix formed with the gamma optimum as given here. So, this is what is finally radiated, although RSS is identity, although this is an R cross R a diagonal matrix because S are all independent. However, what is actually radiated is having this kind of power. So, if you can allocate power in proportional to the channel strength, we can achieve the maximum value of capacity when channel state information is available at the transmitter. On the other hand, when channel state information is not available at the transmitter, the best you can do is to provide equal power and leave the covariance matrix of the transmitted signals to be identity matrix. We conclude our discussion on channel capacity for these two cases here. We would move on further to discuss the effect of correlation and some other MIMO transmission schemes in the remaining few lectures. Thank you.